So, hello, good morning.
Morning, sir.
Morning, sir.
Good morning too. So, okay. So I cannot remember anymore. How many are we? When we were still in, first week or second week. Is this a good number? How many of you? Can anyone say that? How many are we in the first meeting or second meeting? Are we around 13 also or 15, something like that? Or are we
Sir,
around?
if I remember correctly, we are around 20 or 21, somewhere
20?
around there. I'm not sure.
Okay. So yeah, thank you very much. Kasi yeah, I think uh, mas kumonti tayo ng sobra. Like, it's like half only. Okay. Well, anyway, so I hope the others are doing good. Like, worst case scenario is they have COVID. That's why they wasn't able to attend our meeting today. Well, anyway, so let me just open the calendar. Calendar. Okay. So let me just share my screen. All right. So can you guys see my screen now? Okay. So we still have how many meetings left? This one is Monday, Thursday, right? So today is 9. Our next meeting will be on 13, Monday, and then we still have one more meeting on Thursday, which is 16. And then your midterm exam will be on 20. Okay, that would be September 20. So we still have 2 meetings left. And then this is already our last topic for the midterms. Okay, so up to module 3 only. So since we still have like one meeting left, okay, since the 16 Thursday, I always give that one as your free time to do anything that you want. Okay, you might want to use that one to review, to finish all of the activities that your instructors give to you. Okay, so if you guys will agree, we can have a discussion on Monday, but that topic is now for the finals. Okay, so the first chapter of the finals. But of course, that topic will not be part of your midterm exam since that is an advanced topic for your finals. So let's have a votation right now. So I'll give you guys the privilege to those who are here right now. So I'll let you guys do the decision for the entire class. So uh, call this one the majority wins. Yeah, something like that. Okay, so we have a total of 14 participants deduct me. So there will be 13 participants in total. So if you will agree that we're going to have a discussion on Monday, okay, which is the Clippers. So just give me a thumbs up. Or you can just type on the chat box. Okay. None? Walang may gusto? Okay. About I reverse it. To those who disagree, okay, just give me a thumbs up. Those who disagree, okay. In other words, you're going to have 2 free meetings. So 13 and 16. So 1, 2, 3, 4, 5, 6, 7. Okay, so 7 is already enough since there were only 13 of you guys. So it's already the majority vote. Well, anyway, okay, so this is already our last meeting for this week, and then for the entire week next week, okay, that will be your free time, okay. And just in case that you guys have questions maybe or clarification, so just message me anytime, okay. So as soon as I will see your message, then I will reply as soon as possible. Okay, anyway, so let's just have a short walkthrough again on your week 3 module 3. So again, this is where you can find topic learning outcomes, the list of topics, okay, and then the lecture presentation itself, and then the YouTube links that I did found on the YouTube, which I think is super helpful when it comes to understanding more about rectifiers, half wave rectifier, and then full wave rectifier. So you can also check this one, but this one is not 100% reliable since this one talks about more on the formulas, I guess. Uh, yeah, like this one. So how did we get this formula? Okay, where this one came from, Vm divided by 2, Vm divided by pi, okay, and then the rectification efficiency. But most of them similar with our slides, okay, on the PDF. So yeah, you can also check this one out just in case that you need more information regarding with the rectifiers, okay. So this one came from Indian Institute of Technology. So IITD. And as usual, I prepared here, okay, a short pieces wherein you can uh, you have unlimited attempts. Okay, you can practice as much as you want. So in here, I've included three like quizzes that came from quizzes. Okay, so this one is a good website when it comes to basics. So I've also prepared a little bit much more harder, a little bit na much more pa. Okay, anyway, so for the first one, which is the engineering 4300, okay, so this is like a PDF also wherein there is already the answer right here. Okay, so just read this one and then this is the answer. Just read this one again and then just analyze it and then uh, check why this one is the answer. Okay, so you can cover them one first, like maybe you can print this one out and then erase those first, okay, or just cover them, and then later on you will check or just check if you were able to get the correct answer or no. So we have up to, I don't know how many items, but yeah, so one is a quiz for the diode rectifiers, and then the second one is it's like a PDF also, but it came from a website wherein you can choose your uh, answer, and then if uh, you need explanation why you wasn't able to get the correct answer, you can so just click this hint right here, okay, and then it will give you some tips maybe to figure out why is your answer is incorrect or why is your answer is correct. Okay, this one is up to 99 100 items. Okay, so this is a perfect website also to practice your knowledge when it comes to rectifiers. And then the last one, so if it's blocked by the canvas itself, so just click this link right here and then it will lead you to its real website or the real source. Okay, so in here, you cannot choose your answer, but let's say your answer in number one is, let's say, letter C. So you can check them out by viewing the answer. Okay, just by clicking this link right here, view answer. Okay, so it will give you the answer and then the explanation why. All right. So I think this one is 10 items. Yeah, up to 10 items. So if those given links are still not enough, then you can visit more on, maybe on YouTube, or maybe you can visit more other articles. Maybe if you can find uh, other articles which talks about diodes and rectifiers. And of course, we're going to have three quizzes. Okay, so you can answer these three quizzes after our discussion, of course. So once you've fully understood everything. And then I have also prepared a case study for this module. Okay, so all of them, their dues will be September 16th. So are we clear so far? Any question or clarification before we start? with the discussion. Okay, so it seems that there is no question anymore. So let us start now with our discussion. So chapter 3 talks about rectifiers. So to make it short, here are the topics that we are going to discuss. So first one is half-wave rectifier, full-wave rectifier, and then the bridge rectifier. Plus one more thing. So I forgot to include here, we have the center tap rectifier. So it's like a total of 4 topics. Okay. But anyway, let's start with the question, what is a rectifier? So again, to make this one simple, a rectifier converts a voltage source from AC to DC. Okay, so this rectification process is like symbolizes the word straightens. So when we see rectification, it straightens the direction of the current. Okay, and the opposite of that one is of course the inverter. So if we have from AC to DC, we also have from DC to AC. Wherein, of course, you have a source of DC and then you're going to have an output of AC. Okay. So yeah, and then here are now the types of rectifier. Okay, so let's start with half-wave rectifier. So the one that you're seeing on the left side is the voltage input. Okay, or let's just say that this is the voltage that is coming from our outlet. Okay, so we have a full wave AC. So we have the positive side and the negative side. And then as I guess can see right here, we have 0 to T. So this one only means that this is a one cycle. So one cycle composes of a positive half uh, half cycle and then the negative half cycle. So of course, it has a T divided by 2, which is the middle of it, wherein at this point, we have a 0 reading of voltage. So for example, we have, let's see, 0 to 220 volts. So this one is 0 and then it's incrementing by 10, maybe 10, 20 until it will reach the VM. So what is this, the VM? VM is the maximum voltage or maximum peak value, okay? Or you could just say VP, okay? It's the peak value of your voltage input, okay? And then this VO right here is the voltage output. So yeah, this one is the AC input that will be coming from this side. And then, of course, it will pass through this diode, which is if you are going to check this one. So we have a positive to positive connection and then negative to negative. So remember, if we have that kind of connection, so that one is a forward bias. So if we have a forward bias, this one is just simply a closed switch. Okay. So in other words, whatever is our VI, that is also the reading of our VO. Okay. So yeah, that's it for the introduction of what is VI, VM, and then what is the 0 t divided by 2, and then this t right here. Okay, so let's have an actual example. Now, what if our diode is an ideal diode? So again, if it's an ideal diode, we don't consider the threshold voltage, okay, and we don't consider also the bulk resistance. So if it's a forward bias, it's just simply a closed switch. So in here we have this kind of polarity, okay, so positive to positive and then negative to negative. So of course, it will form a forward bias. So as a result, this is a closed switch, and then our positive cycle now can pass through this circuit. So as a result, we have a reading for the positive side. But what if we are now at the point wherein we have the negative cycle? Okay, so just interchange the polarity of this one. So negative on the upper and then positive on the lower side. So in here, we have a connection of negative to positive and then positive to negative. So as a result, this will become an open circuit. So I'm not just sure if, yeah, okay, this is not the uh, reverse bias. So again, if it's a reverse bias, then it doesn't permit any current to flow in here. Okay. So that's why in a negative cycle, we have a reading of 0 volts. Okay, so this one now composes the one cycle. And as long as you were able to get the computation on the first cycle, it will just repeat the process repeatedly or unlimitedly. Okay, so the next one is the same with this one. Okay, so we'll have another uh, positive value and then flat line for the negative value, positive value, and then flat line, and so on and so forth. So this graph is already enough to define the uh, say the waveform of or the wave output of your circuit. Okay, so during the t divided by 2 to p, the polarity of the input signal Vi becomes negative, which causes the diode to turn up, resulting in an open circuit equivalent across the diode terminals. So if you are going to solve this one via Ohm's law, of course, you will have a zero current. So 0 times R, so any number that's multiplied to 0 is 0. So that is why we have 0 volts reading on the negative part. Okay, so as its name, trying to imply, trying to say, we have a half wave rectifier. Okay, so it's either pure positive only or pure negative only. So the other half will be neglected. Okay. So are we clear so far up to this point? Okay, so again, if you have a question, so just let me know. Okay. All right. So this is the complete graph. Okay. So this is one cycle, one cycle. Okay. So this is the complete cycle of the voltage input. And once it passed through a circuit, which is something like this, okay, like a circuit for half wave rectifier, you will have this kind of graph. Okay, positive only, and then the negative will be neglected, and then positive again, and then the negative will be neglected. So in here, since we have an inconsistent value of uh, voltage, so you can get the VDC or the average voltage of this one by using this formula. Okay, so we have VDC is equal to 0.318 times VM or the VP value. So with that, you will be able to get the average voltage of this let's say of your voltage input, because that one always depends on your voltage input. So of course, if you have a high voltage input, it will give you a higher average. Okay, if you have a lower voltage input, then of course it will give you a lower average. Okay, so that one is dependent on the VM. All right, so what if we are going to use a silicon diode? So what is the effect of that one on our graph? So before, it's just a pure, let's say, from 0 to peak value and then going down to 0 and then to peak value again and then going down to 0. But since we are now considering the threshold voltage, so every time that the current will pass through here, so we have to account this one. So in other words, uh, we're just going to deduct this voltage threshold. So for example, if we have a 20 volt VM, so just deduct this 0.7, then you will have 19.3 volts. Okay. And then remember our graph in, a forward bias with a voltage threshold. So it will not go up or it will not rise, okay, as soon as possible. So it has to consume the threshold voltage first, okay, like for 0.7 volts, and then at exactly 0.8, that's the only time that it will go up, okay, and then it will reach the 19.3 volt or whatever is the computed peak value, okay, and the same at this point, okay. So at this point, of course, it will consume again another one, since this is another input for the negative part. But since in this kind of circuit, we don't have a negative result, so that is why we only have this one, okay, which is only affecting the positive cycle. So for the negative cycle, it won't affect that one, since that is 0 anyway. Okay, so yeah, let's have real example later on for you guys to see the real waveform and then the real values of our VO. But anyway, before that, so while the diode conducts during the rectification process, it generates a DC output that carries a fixed voltage level for the voltage difference. Okay, so before we go to the DC or the VDC, so in order for you to solve for the VO, okay, we have this formula VI minus VT. So this one is also the same with VM, okay, minus VT. Okay, so as you guys can see, whatever is the value of our VI, that is also the same with your peak value. Okay, but then don't get confused on that one. When you say VI is equal to VM, it's just the peak to peak value. Okay, so VI still will be coming from 0 until it reaches the VM. Unlike VM, it is the peak value already. Okay, so thus VI must be greater than VT or VM must be greater than VT. So in other words, in order for you to make this one work, okay, or in order for you to have a waveform like this, your VI must be greater than your voltage threshold. Okay, so if you only have a voltage source of 0.6 and below, then you won't be able to, conduct or pass through a current through this diode since it only 8, okay, or it only consume that voltage of yours, okay, if it's super low. Okay, so let's now talk about the VDC. So what is this VDC again? So VDC is the average DC output formula with the threshold voltage of the diode. So if it's an ideal diode, then you don't have to consider the voltage threshold. So just multiply that one to our VM. So 0.318 times VM. But if you now have a voltage threshold wherein, so you have to consider that it's a silicon or a germanium, then you have to deduct that one on our peak voltage, okay, or maximum voltage. So we still have the same formula, so it's still 0.318 times Vm, okay, but it's now has an additional one which is minus Vt. Okay, so are we clear so far regarding with the average DC output? Okay, so I would say that this is actually the only formula that you need to memorize, because when it comes to VO, okay, you can get that one by applying KVL, okay, or just by simply applying Ohm's law. Okay, so you will arrive with the same formula, which is like this. Okay, so let's have an example for half bridge rectifier. So problem number 1, consider the diode as an ideal diode. Evaluate the output VO and find out the DC magnitude of the output for the circuit design shown below. So we have here the voltage input. So we have a peak-to-peak value of 20 volts. So we have positive 20 volts here. And then, of course, we also have negative 20 volts. Okay. So, of course, initially, we have this polarity, positive and then negative. And if you guys are going to take a look at this one, positive is connected to cathode, okay, or negative. So positive is connected to negative, and the negative is connected to the positive. So as a result, you guys already know what will happen. So for the positive cycle, okay, we have a 0 reading since this will become a reverse bias. But when it comes to negative cycle, which is now the negative and then positive on below, so we have a connection of negative to negative and then positive to positive. So this will permit a current at a negative cycle. So as a result, we'll have this kind of waveform. So for the positive, it's flat, okay? And then for the negative, we have the value of negative 20 volts. And then 0 again, and then negative 20 volts, and then 0 again, okay? And if you guys are going to compute for the voltage output, since this one is an ideal diode, so we don't have a voltage threshold, and then we don't also have a bulk resistance. So Vm minus Vt, is equal to 20 minus 0 is equal to 20 volts. Okay, so if it's ideal diode, Vi is equal to Vo already. Okay, as simple as that. And then for the VDC, so you can use this formula. Okay, so you can just stick with this formula actually. Okay, 0.318 times Vm minus Vd. Okay, it's just that we have an additional one. So if we have a negative result, then your average must be negative also. Okay, so that is why we have a negative sign right here. But if you only have a positive result, then of course your average must be positive also. So just remove this negative right here. But since we have negative, so we have to put negative in here. So 0.318 times Vm minus Vt is equal to negative 0.318 times 20 volts minus 0 volts is equal to negative 6.36 volts. Okay, so this is the average DC output of this voltage input right here. So are we clear so far? Were you guys able to follow the example number 1? Okay. What about the others? Mr. De Mayo, Mr. Santa Cruz, Mr. Awas, Mr. Alburo, Miss Garcia, Miss Magay. So just in case that you've missed something or you wasn't able to understand this part maybe, so just let me know, okay? All right, so let's now move on to the second example. So this one is still the same example. It's just that instead of a ideal diode, let's consider the diode as a silicon. Okay, and then we still have the same unknowns or the things that we need to find. Okay, so we have to find the VO, we have to find the DC magnitude, and then we have to find the, okay, it wasn't mentioned here, the waveform, but anyway. So yeah, we have this input, okay, which is a 20 volts peak to peak. So we have 20 and then negative 20. And then in here, it's not just the diode anymore, since we have to consider the voltage threshold of this one. Okay, so we can actually copy this one and then just put here negative 0.7 and then here the same 0.7. And then you will get the correct result. So very obvious. For the solution number 2, it's 20 minus 0.7, so 19.3 volts for the voltage output. And then for the VDC, so we just have an additional one, which is the voltage threshold. So 19.3 times 0.318 will have a reading of negative 6.14 volts. Okay. So are we clear with example number 2? Okay. So super easy to understand when it comes to half wave rectifiers. Okay. So let me just explain this one, the drop in output DC. So here is the first value of our first example. We have a reading of 6.36 volts, and then we have the reading of the second value, which is 6.14 volts. So if you're going to get the difference of those, we'll have 0.22 volts. So what does this one mean? So the drop in the output DC voltage due to the 0.7 voltage factor is around 0.82 volts or approximately 3.5%. So in other words, okay, so in real world, of course, a diode always consumes a certain amount of voltage. So expect that, in your voltage input, you will always get a 3.5% loss, okay, or drop, okay, if you're going to pass through a certain diode. Okay, so that is a fixed value. So if you want to, get 100% result of your voltage input, then you have to put an extra. Okay, so just compute the 3.5% of that one, and then just add that one to your voltage input. So with that, you'll have the reading that you are, you're expecting, okay, or you want to have as a reading of your circuit. Okay, so remember this 3.5% drop per diode. Okay, that is just one diode. But what about if you have 2, 3, 4, or 5 diodes? Or what if you have 10 diodes in that circuit? So expect that you'll have 35% loss if you have 10 diodes. Okay, so yeah, that's pretty much it for the half-wave rectifier. So we have the number one, which is the ideal, and then the second one, which is the non-ideal, okay, or the silicon with the use of a voltage threshold. So the next one is the full wave rectifier. So this one is also super simple. So as its name is trying to imply, you can have a 100% level, okay, or 100% output by applying a full wave rectification. So in here, you're going to have the positive and negative voltage output. So how will you achieve that one? So you can use this 4 diode bridge rectifier. So this is the easiest way in achieving to have a full wave waveform or full wave output. Okay, so we have 4 diodes and then 1 resistance, and then you have to follow the correct polarity of your diode. So it must be the same as this one. So for your D1, D2, D3, and D4. Because if you're going to interchange D3, then something might not work, okay, as properly. Okay, so what is this 4 diode bridge rectifier? So when the positive input cycle progresses through the period, t is equal to 0 to t divided by 2, okay, or t halves, the polarity of the input AC signal across the diode and the output from the diode are as represented below. So during the positive cycle, so let's have the positive and negative polarity right here first. So if you guys are going to take a look on this one, let me just get this one. Okay. So of course we have this flow of uh, current right here. And then at this point, of course, you will split into two. Okay, so some will go here and then some will go here. So since we have a positive to negative connection, okay, and then negative to positive, so this will turn off, or this will give us a reverse bias connection. So as a result, it will go back here, and then it will now only flow on this diode right here. So if you guys are going to check, we have a positive to positive connection and then a negative to negative connection. So as a result, this will be turned on, and this one now is in a forward bias. So all of our voltage input is now at this point. So of course, again, it will split into two. So some will go here and then some will go here. So if you guys are going to take a look at this one, we have a positive to negative connection and then negative to positive. So as a result, this will become a reverse bias or an open circuit. So again, it will go back here and then it will now only flow on this direction. Okay, so as a result, our VI now is equal to VO if this is an ideal diode. Okay, and then at this point, okay, it will now flow here. And then since this one is an open circuit, so of course it will now only flow at this direction. Okay, and then again, this one is now also an open circuit, so it will now flow here and go back to its main source. Okay, so are you guys able to follow the uh, flow of our current in this diagram? Okay, great.